Okay, so Arash, we are good to start now, right?
Sure, thank you.
Okay. So today's session is about an introduction and a fair bit of overview and deep dive around cloud native storage. And I myself, Shantanu, and I work as an SRE at Cloud Sky. So before starting with cloud native storage, the first question which should come to our mind is why do we need cloud native storage, right? So here are some few questions which you should ask yourself why you need cloud native storage. The first one is like, is your storage platform independent, right? So if at some point in future or in some point in future you see that your infrastructure is going to be changed, is your storage will your storage also change with the platform? Ideally, cloud native storage should be independent of the platform. Next is, can your uh, non-cloud native storage scale to the level of hundreds or thousands of containers, which will request volume simultaneously? Uh, can it handle the amount of request which our containers will make? Okay. The next one is operational side of your storage systems, right? So we know that in the old style of storages, there was a considerable operational overhead on the storage system. So ideally, your cloud native storage is kind of automates the operational side of your storage. So you don't have to manage storage on the lower level. Next one is role-based access control. So again, this is very important because in your cloud native world or in Kubernetes ecosystem, everything requires or it should be done via role-based access control. So for security reasons. So is your storage providing that kind of features? The last one is like, can your storage provide different capabilities based on the workload type? So for example, I have big data workloads, so computing intensive workloads. So can your storage give a different kind of performance for that use case as compared to the other stateful apps or other Java based apps or whatever apps you're doing? So your storage should be flexible enough to provide different level of storage capabilities based on workload. Hello?
Hello, Shantanu.
Yeah, just a second.
Okay.
Hello?
Yes, we hear you again.
Yeah, sorry. Sorry for that. So I'm back. So these are the first questions. Then next is, this is just a brief overview of cloud native storage landscape. So there are some familiar faces starting with Rook. Then we have StorageOS as well as OpenEBS as well. Some of the popular open source projects as well as Portworx, which provides enterprise solutions for cloud native storage. Next is, now we have seen that what are the questions which we should ask before saying that we need storage, cloud native storage. So the next question which arises is, what should your cloud native storage system provide in terms of features or reliability? So the first one is, like I said, that it should provide different storage capabilities based on the workload. So that is the first thing which should be covered by the storage system. Yeah, it should be able to provide object storage, block storage, or NFS storage when required. The next one is automation and abstraction of storage infrastructure, right? So we have already discussed that there used to be a considerable overhead on maintaining storage systems. So what I would expect my cloud native storage system to provide is an automation and an abstraction of the management of storage infrastructure, so that I just need to be able to manage my underlying infrastructure by just interacting on an abstract level. Now, next is API-driven storage management. So we know that everything happens through the API in Kubernetes. API calls are used almost everywhere. So I would normally expect my storage system to be provisioned based on a single API call. That is the expectation from the storage system. The next one is platform independence. Obviously, we discussed is that the storage system should be independent of your underlying platform, so that whenever you decide to change the platform, you don't have to change the storage system. It stays as is. Next is dynamic provisioning. So dynamic provisioning, we need dynamic provisioning in Kubernetes because resources are provisioned dynamically, and a lot of the applications require volumes to be provisioned automatically. When you have tens of hundreds of pods requesting volumes, then you cannot do it manually. The provision should be done dynamically. The last one is provisioning storage in container orchestrated native way. So this is the thing which has been possible by the introduction of container storage interface, CSI. So using this CSI, you can interface your storage system with different orchestration container orchestrators like Kubernetes, Docker Swarm, Mesos. So this is what the storage systems should provide. So this is a very brief overview of storage system workflow in Kubernetes. So as you can see, it all starts with deployment or a stateful sets from the left-hand side, leftmost side. Then we all know that deployment triggers replica sets, and replica sets will create pods depending on replicas. That is fine. But then the next tricky part for storage system is PVCs. Right, so you can have read write once PVC, read write many. So read write many PVCs will require your storage system to support NFS provisioning. And at the end of all of this, we have storage classes. So storage classes are provided by the storage system, so that you can use the storage classes to provision volumes. This is a little bit on the detail side, along with a few YAML code. So again, it starts with pod. Here you can see that we can specify the PVC persistent volume claim, the claim name, success login. So it will point to the persistent volume claim with the same login. And the thing to note here is access modes. This is read write once. So this PVC can only be mounted by one pod. And yeah, so we are requesting 64 GB of storage. The storage class name, for example, is OpenEBS host path, and this is the storage class YAML, a simple YAML file. The storage class YAML files can differ based on the storage system. This is for OpenEBS, but it will be different for Rook or StorageOS. And this is the real persistent volume, which was claimed by, which was created by PVC. These are some notable cloud native storage providers as of now. So in terms of open source, we have three notable cloud native storage projects. The first one is OpenEBS, Rook, and Longhorn. So OpenEBS is a storage engine of OpenEBS is kind of using Longhorn internally. And in terms of closed source, so we have this storage providers with Portworx, StorageOS, K8s. So what you get with this closed source storage providers is reliability and stability. So we will start with the, in this session, we will only look after open source storage providers, mainly OpenEBS and Rook. So we'll start with OpenEBS. So OpenEBS provides container native storage. CAS, they call it CAS because, well, as per the StorageOS folks, cloud native storage term is used widely, and the real meaning of cloud native storage term gets distorted. So it is OpenEBS terms itself as a cloud native storage, and yeah, it is multi-cloud, run anywhere, so platform independent. That is the first thing, and it has integrated metrics collection with Prometheus and Grafana. So the metrics of OpenEBS are exported to for the monitoring, and it has support for multiple storage engines, mainly Jiva, Systore, and local PV. So this Jiva storage engine is is using Longhorn internally, and Longhorn is Rancher's open source cloud native storage project. This is storage engine comparison between multiple with OpenEBS. So as you can see, we have Shiva, Systore, and local PV. And on this side, we have features, lightweight and user space. Of course, yes. Thin provisioning is provided in Systore. You have there are many features, and all of these are listed on their OpenEBS website. If you want to go into complete details of these features, you can visit the website. So we'll start with the OpenEBS architecture. So this is a high level overview of how OpenEBS components are stacked towards each other. So we have three components: cluster components, node components, and again cluster components. But the thing is, like, we have API server which responds to the request of provisioning storage systems. Then we have an NDM operator. NDM is node disk manager. So with use of this NDM, we can create a pool of different disks and provision storage by creating PVCs. So you don't really have to do anything different. Just request the storage, and the storage will be provisioned by the pool which has multiple disks. That is the NDM operator and NDM daemon set, which runs on all nodes. Then we have three different storage engines: Systore, Jiva, and local PV. So control plane mostly consists of these components, and data plane has storage classes. So this is the overview of control plane systems. So as you can see, we normally interact with all of these control plane components via API calls, or let's say CLI. So with MySCTL, which is an OpenEBS CLI, or kubectl as well. The important components here are OpenEBS API server, and this is Kube API server. So The interaction happens between OpenEBS API server and Kube API server for receiving requests for provisioning of storage and handling them. Then on the rightmost side, we have infrastructure management components like monitoring, logging, alerting. Everything is metrics are exposed via Prometheus. This is the overview of PV provisioning, how persistent volumes are provisioned in PV in OpenEBS. So as I said that it all starts with the PVC. So PVC mentions the storage class then interacts with OpenEBS PV provisioner, and then Maya API server, and then following to the Kube API server. So at the rightmost side, we have different pods. So the idea with OpenEBS storage is your storage is managed by containers itself. So when you provision a storage in OpenEBS, you see that you have 2, 3, or 4 pods provisioned for maintaining your storage. So this is just an example. So OVCTRL is the control or the main pod which is iStatic target. Then you have 3 replicas for high availability and data consistency. So in case the controller goes down, then another replica can be promoted as a controller and storage remains safe. This is API server internals. So the API server components are API server, policy engine, and volume parameter group. So again, it all starts with the PVCs. So PVCs obviously mentioned storage classes. So the request is sent to the OpenEBS API server, then it handles internally the API request, the policy engine, obviously, and again, the parameters which are specified for provisioning volumes. So these are done via storage classes. And this is the part where your pods are provisioned, controller service and controller deployment. So as I said, that we have one controller pod and multiple replicas. So this kind of thing is managed here. Controller service, and then it creates a controller deployment and then replicas deployment. This is volume exporter data flow. So this is good to know. You probably won't interact with it directly, but it is good to know so that in case. So we have, like I said, that we have metrics are exported by Prometheus. So as you can see, we have the Prometheus client, Maya Prometheus or client or Cortex client. Maya Online is a different service for as a GUI service for visualizing OpenEBS components and cluster components. It is helpful for monitoring the health of the OpenEBS deployment overall. Or if you have your own Prometheus deployment, it can be also seen via Prometheus Grafana. So these volume exporter sidecars are attached via the APIs. This is mostly for CStore. As you can see, mostly it's all about CStore. CStore is a different storage engine which is used for using sparse disks. It is more production ready, but it requires dedicated disks, unlike Jiva. These are volume management sidecars. So these sidecars are these sidecars are responsible for maintaining the volume related operations of OpenEBS. As you can see, everything, all of these steps are automated here. So you don't really have to manually deal with all of these steps on your own. And this is a very key component of OpenEBS called Node Device Manager. So as I said, like if you have multiple disks, then what Node Device Manager does is it creates a single pool of multiple disk, and then you can provision storage via a single PVCs, persistent volume claim. So you don't really have to specify which disk you want to provision or which network the disk should be using. NDM manages it, manages the storage pool on its own. So the key component here is NDM operator. So NDM operator is stores its data into etcd, block device custom resources, and these are responsible for discovering and adding block devices on their own. As you can see, consider disk as these as single nodes. So if we have 4 nodes here, then all of the nodes will run NDM daemon set, and they can have local disk or externally attached disk as well. So NDM operator will continuously look after the pool of disk which are present, and if any new disk is added, it will automatically update itself and make it available on the pool, storage pool. We will see a few of these components live in the demo. Then for now, we will move towards our next open source project of cloud native storage, which is Rook. So Rook also provides cloud native storage. So Rook was started a little bit earlier than OpenEBS, and it also has multiple storage providers: ceph, V1, ceph is stable, EdgeFS, which is in beta, and then Cassandra, CockroachDB, Menu, and FS. All of them are in alpha. So Rook normally relies on Flex Volume plugin to manage storage attachments. It is the most popular storage provider in Rook is ceph. So you can use ceph internally via Rook, and Rook manages ceph for you. As mentioned here, so ceph clusters are created by Rook custom resources, custom resource definitions. So you don't really have to directly deal with ceph clusters. You just have to deal with Rook, and Rook will manage ceph clusters for you. This is the architecture of Rook. So as you can see, we can use kubectl to actually request storages via APIs, and the important components here are Rook operator and Rook daemon. So Rook operator is Rook operator directly interfaces with the Kubernetes API, and Rook daemon runs on all the nodes, obviously. So supported here are ceph, ISAG, NFS. Then you have Rook agent, Rook agent, and then every kubelet have Rook volume plugin. So Rook agent interfaces with Rook volume plugins, and when a new storage is requested, it will provision the volume and attach it to the pod. This is ceph-based Rook architecture, ceph specific. So as you can see, we have multiple applications here, and applications will ask for persistent volumes, PVCs. These are Rook pods, and then as I said, we have Rook agents and Rook operator. So these agents will be responsible for provisioning and maintaining ceph components like mons, OSDs. So you don't really have to do this provisioning of ceph clusters and storage on your own. Rook agents will manage it for you. So these are very small GitHub stats for OpenEBS and Rook. This might have been changed, but I think this is pretty good in terms of the cloud native landscape. These two are probably one of probably very popular open source projects, as you can see, with numbers of stars and forks almost similar, not much difference. And one last thing, CSI. So as I said that the storage should be available in container orchestrator native way. So what I mean is the CSI. So CSI is an initiative for unifying storage interfaces for different orchestrators like Kubernetes, Mesos, Swarm, etc. And what this brings is like a single CSI implementation can work with multiple orchestrators. This is important because again, it provides a flexibility and independence in terms of platform. So you can change your orchestrators and you can still keep your storage system as it is. This is just a small overview from Cloud Native Con EU, where this is just a small architecture. Like on the top side, you have multiple container orchestrators like Kubernetes, Mesos, Docker, etc., etc. Then you have pluggable storage interface. This is what we call CSI, which stays between the orchestrators and storage providers like EBS, ceph, Portworx, etc. So before CSI, this is how the storage provisioning used to work. You have a Kubernetes core, masters, like nodes. Nodes will have kubelet. So here you will have a volume plugin. So in terms of Rook, we have flex volume plugin. Just an example of this. And this volume plugin will be responsible for provisioning storage. With now, this is the architecture with CSI. So again, you have external components in Kubernetes stream and external components which are third party. So CSI components are in the external third party external components. As you can see, CSI identity, CSI controller, CSI node. So these nodes will actually interface with the external component stream of the Kubernetes driver register, external provisioner. So all in all, this will be this will provide platform independence from the Kubernetes. This is showing Kubernetes right now, but yeah, so as you can see here, the storage interface will remain same. Container orchestrator might change. So this is the current status of CSI implementation in multiple projects. So OpenEBS, it is under active development. It is available, but it is under development. So Rook, it is stable from since 1.1 release. StorageOS CSI implementation is available. In fact, it is the recommended implementation with StorageOS, and with EBS, it is still in beta. Next is you will have a small demo. Okay, so the demo involves OpenEBS only for now, but this is just to give an overview of how to deploy or how to use storage systems in Kubernetes, cloud native storage systems. So I have one infrastructure cluster and I have OpenEBS installed here. OpenEBS. And the deployment of OpenEBS has created multiple storage classes for me. So this is local storage, this is C-store sparse, this is OpenEBS Jiva, and this is snapshot promoter. So this OpenEBS Jiva storage class, we will see. Okay, as you can see, there are no persistent volumes with C-store sparse. And this is the OpenEBS namespace where OpenEBS is set up. As you can see, we have OpenEBS API server, OpenEBS node disk manager, and OpenEBS provisioner as well. So we'll just try here by creating a stateful state deployment with our new storage classes. Yeah, so for now I will use OpenEBS Jiva because this cluster does not have separate disk which I can use, which can be used for provisioning via store. Okay, all good. So as you can see, we have Redis master setup and Redis slave. Right. So the key thing to look after is these different pods which were created along with this deployment. One is controller and one is replica. So these pods are responsible for managing the OpenEBS storage for Redis master and Redis slave. All of them are running. Right. So all of this provisioning of volumes is being managed and maintained by OpenEBS pods. So it's like your storage is container native. So because containers are responsible for creating and managing storage for you. That is why container attached storage. Yeah, and this is C persistent volume, which was automatically created by OpenEBS storage class. OpenEBS Jiva default 8 GB size, 8 GB size. And now we can see a persistent volume claim is provisioned by storage class. So that the key thing is like for OpenEBS to run on your Kubernetes nodes, the nodes should have iSCSI package installed. So this is the OpenEBS Jiva storage class. This is cache.openebs.io config. This is OpenEBS related config. The important components here are replica count, which are 3. Storage name is storage pool. Then we can specify, we can create different storage pools. We can create different storage class pointing to different storage pools as well, depending on requirement. And this is probably it. So you don't really have to go into your storage class or storage systems console, provision volumes, and then attach it here. Everything is managed here by just specifying the storage class. So yeah, that's it for now. So if you have any questions, we can discuss.
Okay, thank you very much, Shantanu. Great. So are there any questions from you, nice guys? You can unmute yourself or write your questions in the chat. But I have a question. And so I know on this cluster, we are using Flannel. And let's say we discussed that, I think, yesterday through chat. And I asked a question in different Slack channels by OpenEBS. How do I separate the storage network and with my CNI, my network plugin? So as I got it, with Flannel is not possible, perhaps with Multus. But how do this OpenEBS installation uses the operator. I'm not fully sure if my question is right. Is there any way so that I can tell OpenEBS by the provisioning to use another network interface to separate my management network, my workload network, and the storage network?
Okay, so as I noted, by default, these network interfaces are managed and created by Docker itself. The virtual interfaces, I mean. So I think with Flannel, I'm not really sure, but Flannel normally discovers all the network interfaces attached to a node.
Okay.
And I'm not really sure if we can specify the network interface name directly in persistent volumes or inside deployments. It is possible. I think it is possible via Multus CNI or CNI Genie, because I saw a few blog posts and they were just specifying interface name inside annotations.
Okay. Yeah, Martin wrote maybe with Calico would it be possible? Yeah, but there are some problems there. I have to dig myself more deeper into that, and yeah, there was discussion. Maybe the a custom resource definition is going to be developed by the special interest group Plumbing CNI for storage and CSI and CNI and so on. I think the container runtime like Docker Container D, Cryo, or whatever, they shall be aware of this change, and the deployments of a stateful set we shall tell him somehow to use another CNI. You can use Flannel. Let's say if you have Canal, you can have Flannel and Calico. And only the question is, how can I tell my stateful sets to use Calico and all other should use Flannel? Okay, there is a question. What does near storage performance mean? Is it similar to data locality?
Kind of, yes. So near storage performance means it is more related to what the performance you will get with the new local PV provisioners.
Okay. How do these systems handle a bad pod?
I think these systems, okay, interesting. So normally the case of handling bad pods are done on the cluster level and not on storage systems level. So if a pod is not working, the Kubernetes replica set will identify that I don't have 3 pods, which I'm expecting. So it will normally manage it. So storage systems don't really need to deal it.
Okay, thanks.
I think I'm asking more of it. Like, can you hear me?
Yeah.
Okay, so when I ask how the system handles a bad pod from a storage perspective, if I have a pod that has storage connected to it, and let's say the pod goes bad, I'm gonna have to rebuild a pod. It might not be in the same location. Do I have a snapshot that happens before, and then I move the snapshot? How does, like, I'm saying, like, or even does that move it from, from, if I have to have it from one cluster to another, I want to have my pod be seamless and handle events that might cause that pod to not be available, right? So does this give me, like, from a storage perspective, if we use a standard storage, of course, that doesn't work like that. Whereas, the cloud native storage is supposed to actually give us more functionality, right? So does this allow us to do snapshotting, move the snapshot, bring it right back up, like maybe like a Portworx does, or?
Yeah, it's possible. So before going to snapshotting, I will say that we have multiple replicas. Like I said, that we can specify the number of replicas for handling our storage and replicating our storage. So with normal OpenEBS storage class like Jiva, the default replication is of 3. So you have one controller pod and 3 replicas of the controller pod. So you have identical data across these pods. So if any pod goes down, a replica can be promoted as a controller pod.
And you can use it for backup, either Velero from Heptio or now part of VMware. And there is another commercial tool named Custom, a very nice tool which can handle backup and restore and disaster recovery for you. We played with it, it looks very nice, but Velero is as well. Velero is open source. You can migrate if you are using cloud native storage, let's say on bare metal, like this environment with Rancher. You can migrate your pods, your stateful sets from bare metal into AWS, Azure, whatever with Velero. And it works really nice. We did that for sample apps with Kafka on our environment, and it worked.
Okay, I have received one more question. So the question is, like, can you talk a little bit more about how this will look in multi-cluster setup? And the next one is, how do we do that in multi-cluster setup? So do we have a separate storage cluster in multiple clusters, or how does it done? And another one along with it is, what should be the consideration we should take into in terms of latency and performance with storage? So honestly, I think the multi-cluster setup of storage systems is more like an architectural decision which should be taken, I guess. Arash, you can also help with this.
What was the question?
The question was, how does the storage systems work with multiple clusters? So do we set up a different storage system on different clusters, or do we have?
Sure. You don't have multiple cluster support with that currently. So
right.
You can use in Rancher 2.3, the latest version, multi-app, multi-application support. It means if you want to, but that doesn't answer exactly what you are meaning. So to have cluster-wide, multi-cluster-wide support, you can deploy the same app, let's say OpenEBS is an app as well, on different clusters at the same time, but they are totally independent. Only the nice thing is you have, if you want to update these apps, you can do it or with a single click, right?
Right. Also, if you have a storage system which is interacting with multiple clusters, then you have to deal with latency as well, because when you have multiple Kubernetes clusters, we are talking about federation. So with federation, we have to set up networking between multiple Kubernetes clusters, and then we are putting storage system on top of the network system. So I guess the latency should be a little higher in this case.
Okay. Yeah, the next question here from Yuan is it easy to manage different kind of performance storage at the same time? I mean, for example, I would say my app 1 needs a fast storage, but my second pod doesn't need a fast storage.
No,
Yes,
it's
and
yes, yes,
yeah,
yes, it's possible. So this is possible via storage classes. So you can have two storage classes. One is fast, one is slow, or then whatever you want. And you can specify this storage class names in your application deployments.
yeah, exactly. So storage classes are exactly there to achieve such a functionality.
Would we be able to take a, can you show us your Redis template that you were using so we can kind of see like, because maybe I missed it, but I didn't really see how you were, like with using the catalog, I didn't really see how you're specifying like what storage class you wanted and like, you know, the other parts around it.
Okay, yeah, sure.
So yeah, and I'm not sure who did the installation, but what we recommend, you can deploy when you are using Rancher through the catalog, but I really recommend to define your storage classes in your own YAML files and use your own operator implementation. Either is OpenEBS has a nice operator, or Rook, they have also an operator, and do hold this stuff really as code. So and check it in your Git whatever, so that you know what you have done. Catalog is nice, but that's not really infrastructure as code.
Yeah, right.
I hope that was the answer to your question. Might be I got it wrong.
I guess I was trying to like actually kind of, because I didn't really, like I just saw you guys pushing the catalog button, right, and stuff happening, but I didn't really know, like normally I would have to go set up my own storage class, right? I'd want to know what my PVC is.
Yeah.
And that, like, you
And
know, of
that's
course,
really
drive the rest of the event, right?
Yeah. So if you use, let's say, Helm to deploy your operator, then you can define which storage classes you would like to have. They are simple YAML files, and apply them, and or change them later if something's changed, or if you have an additional storage classes available, and yeah, that's the right way.
Okay,
Okay,
so
with our
as you can see,
I'm sorry. With the storage
yeah.
class, are we able to manage like how much snapshot space is being used, so people won't blow away, you know, like all your storage space, one user?
Yeah. There is a
You
special.
can also define.
Yeah. Go on, Shantanu.
Yeah, so you can also define storage class name with something like this. There is a setting with volume claim templates, or indirectly in deployments as well. So you can use the storage class name setting templates and specify the name here.
Yeah, in a few weeks we will have a meetup. I will hold that. It's about OpenShift Rancher and vanilla Kubernetes, and by this meetup I will show how we are using automation to deploy cloud native storage as well, and with the storage classes, and all of this stuff is available on our GitHub as well. Okay, I think if there is no other questions, I wait a couple of seconds. Would like to thank you for your time on this Saturday, to joining us, and for the nice questions. Thank you very much. Yeah, hope we can meet in person some day by KubeCon, perhaps this year, next year in Amsterdam. And yeah, thanks again for joining. Thank you, Shantanu, for the whole effort, the nice presentation. We will provide the slides. The recording is going on. it will be stopped and provide the link on YouTube, on the Meetup side, and upload the recording to YouTube. Thanks, everyone. Thanks, Shantanu. Have a nice weekend.
Thank you.
Thank you. Bye-bye.
Bye.
Thank you.